Okay, hello everyone. Welcome to the AI Agent Frontier seminar. It's my great pleasure to introduce our speaker today, Dr. Natasha Jaques. Natasha is an assistant professor at the University of Washington and a staff research scientist at Google DeepMind, which places her at the very center of both foundational academic research and its large-scale industrial application. Her work focuses on a very critical and timely issue, social reinforcement learning, especially in multi-agent human-AI interactions. As many of us know, RLHF, or reinforcement learning from human feedback, is a key technology behind today's powerful large language models. Natasha actually developed some of the foundational techniques for RLHF during her PhD at MIT. So today she's pushing that frontier even further. Her talk on multi-agent RL for LLMs bridge her deep expertise in social RL with the challenge of making these models safer and more capable. So her work has received numerous awards, including honors from NeurIPS and ICML, and has been featured in top applications like Science Magazine and MIT Technology Review. For today's talk, if you have any questions, as Natasha suggested, you could actually ask during the middle for the interaction, so feel free. And please join me in giving a very welcome to Dr. Natasha Jaques. Natasha, the floor is yours.
Well, thank you so much. I'm honored to be here and excited to talk with you all today. So yeah, I do love taking questions mid-talk or getting some interaction back and forth. So please, raise your hand or speak up if you have a question. And yeah, today I'm going to be talking about this kind of emerging area of multi-agent RL post-training of LLMs. So I would say that, recently, okay, so to give you a brief overview of what I work on in my lab, we kind of think about social reinforcement learning as how do you make AI better when it's interacting in an environment with other intelligent agents? So this could be your kind of classic multi-agent adversarial training to make your agent more robust. I do a lot of classic multi-agent RL, but I also care a lot about learning from people, learning from humans. So as Ming mentioned, I did some of the early work on RLHF, and I work a lot on how do you coordinate with humans in real time. So, at Google, we did this work on training a robot that could play ping pong in real time with humans using AI. So what I'm excited to talk about in this talk is kind of bringing these threads together, like connecting the two opposite ends of the spectrum, which is actually applying multi-agent adversarial training to fine-tuning LLMs. And the reason I think this is pretty timely is people are getting increasingly excited about RL fine-tuning of LLMs. I think especially with DeepSeek, even though ChatGPT is actually, the application of RLHF, I think for some reason DeepSeek really kicked off in the public consciousness that RL can be so powerful and you can train smaller models and really get great results. So I'm really excited about this too. And I think part of the timing that's going on now is, people are starting to realize that just pre-training on text, on existing pre-training data is kind of saturating, right? So Ilya Sutskever gave this Test of Time Award speech at this year's NeurIPS, or last year's NeurIPS. And he said, data is the fossil fuel of AI. Pre-training is dead, right? And what he means by that is we've already scraped the entire internet and, trained on as many books as we could, illegally download or purchase and burn, right? And there's no data left unless you have some proprietary data, and then people are too scared to train on customer data. So we're not getting any more mileage out of just scaling on data because there's no data left. So we have to have some algorithmic alternative. So maybe RL on some objective you care about offers this next frontier, right? And so there's been this big push on RL for reasoning. But RL isn't magic. So this paper came out that surprised some people. Personally, I don't find it that surprising. But what this paper is showing is when you have a base model, this is looking at solutions to reasoning problems with training with RLVR, so reinforcement learning on verifiable rewards. When you are doing this, your base model is actually already capable of generating pretty much all the possible solution paths through this search tree to this reasoning problem. That's what they're showing here. But what RLVR does is it just upweights the path that is actually correct and leads to the ground truth reward. It doesn't invent a new path. So to me, this should be obvious from the fact that the way RL post-training works is you actually constrain your RL updates with this KL divergence, where you control how much you're diverging from the base model's policy. So you're effectively saying, search within the base model's distribution for something that's highly rewarding. That's what the objective is. And of course, I have to bring this up whenever I can, because that idea of controlling divergence from the base pre-trained policy is actually something I proposed in this 2017 paper. And it's still how we do RL post-training today. Like, DeepSeek experimented with getting rid of that term, but you still kind of need it to maintain consistent language, right? So this is just how these models are trained. So how do we actually learn new and interesting behaviors? Well, I still think there's a lot of hope, because LLMs are really powerful generative models. So they can potentially generate a lot of interesting text that is within the base model's distribution that could help make your model better. And so this is this idea of multi-agent RL. So you take two LLMs and you co-train them. One LLM is generating novel problems. Yes, within the space of what the base model can distribute, base model's distribution, but generating a novel problem, and it's actually targeting the generation of that problem to a weakness in your current learning LLM. And so it's learning to generate data where your current LLM is failing. And by continuing to train back and forth online, you end up getting potentially theoretical guarantees that if this system converges, you're at a point where your LLM that you're training is actually provably robust. And so I'm going to talk a little bit about that in the first part of the talk. And you can potentially unlock continuous self-improvement, like these idea of like emergent capabilities from multi-agent training. And I'll talk about that kind of in the second part of the talk. So just to give you a brief outline, the first part of the talk, I'll talk about this idea of using self-play for safety training. And in the second part of the talk, I'll talk about using self-play for improving reasoning. So starting with the safety training, this is a recent work that we did at UW with a big collaboration here with a lot of the faculty here. Mikkel Liu and Liwei Jiang are the first authors. I think Liwei is going on the job market this year, so everyone would be lucky if they can hire her, so just be aware. But yeah, I'm really excited about this work. And the key motivation here, which I've been writing in a lot of grants lately, is like, we're currently deploying LLMs to over 1 billion people. So if you just look at the GPT users and Gemini users, together they're over 1 billion weekly active users. So many people are using LLMs in their daily workflow, but we actually have no way to guarantee that these models are safe, right? There's no safety guarantees on these models whatsoever. So they can easily do sort of existential risk things, like tell users how to build a bomb or a bioweapon, but they can also do things that corporations really don't want, which is reveal copyrighted or personally identifiable information. And as we've seen in widely publicized incidents, they can say biased, discriminatory or offensive things, right? Or whatever doomsday scenario you're concerned about, we have no way of controlling LLMs to make sure they don't do these things, which seems like a big problem. So if you ask me why this is, like, how can I actually ensure my model is safe? I would say it's because the existing methods for finding and patching vulnerabilities or safety vulnerabilities in these models are single agent or static. So what happens is you first take a static model, like a Gemini model, and you try to red team it. Maybe you pay people online to discover attacks. Maybe you train a reinforcement learning model to search for attacks. But the point is you're red teaming this static model. You then find a data set of attacks and you kind of pass them off to the Gemini team and they try to patch them. But this whole process is this sequential reactive process where you're always kind of finding a limited number of obsolete attacks, and your LLM is just vulnerable to emerging threats. You're not getting any guarantee that you've covered the space of possible attacks, right? But if you were to do this as a multi-agent RL approach, where you're simultaneously updating the attacker and defender in a co-evolving loop, you can actually address this issue. So what you can do is, as soon as the attacker discovers an attack, the defender then updates to patch it online. This actually changes the incentives for the attacker because that attack no longer works. And if the attacker is rewarded for finding successful attacks, it's now getting no incentive to pose that same attack over and over. So it's forced to search for continually increasing attack surface to find points where the defender is vulnerable. And so if you continue to update these two agents together, what we can show is this basically comprises a zero-sum, two-player zero-sum adversarial game. So what we're doing, to be super explicit, is we're having an adversary LLM search for a prompt X, give that to the defender. Defender has to give a response Y. And then you have to judge the safety according to a reward model. And we assume the reward model is given. The focus of this work is not on training the reward model. So we assume you have a safety classifier, you have an RLHF reward model that measures helpfulness and harmfulness, something like that. And then the reward model can assign a score. And then what you're doing is you're actually playing a two-player zero-sum game with this adversary and the defender online. So it's a min-max, two-player zero-sum game between the adversary and the defender. What's the cool thing about two-player zero-sum games? Well, you can leverage this giant history of work from game theory to show that, well, this game has a Nash equilibrium. And what is the Nash equilibrium? The Nash equilibrium is a point where for any prompt X that the adversary can pose, the defender is able to respond safely by maximizing the reward. And you can think of it because we have a proof in the paper. It's pretty simple, but it's basically just inheriting the concept of a Nash equilibrium. But also you can think of the fact that the defender gets the last move. So the defender is always able to maximize the reward of the response given the prompt that it was given. And maybe I'd love to get some audience interaction. Why is it the defender always has the option to respond safely? Does anybody know? Is anyone brave enough to speak up? Feel free to type in the chat if you're feeling shy. Everybody went to sleep.
I mean, they could choose to give no response, which is always safe. It's like a.
Thank you. I appreciate that so much. Exactly. So the defender can always just refuse to answer, which is safe, right? It's not useful, but it's safe. So you can always show that the defender will be safe for any prompt, but that does introduce a complication, right? We don't want the defender to come up with the spurious solution of always refusing to answer. So I'll show how we address that in a second. But how do we actually do this in practice? And thank you so much for speaking up. I really appreciate it. So what we do is we actually do self-play. The reason we do self-play is because of the memory requirements. It's expensive to do RL post-training in terms of GPU memory, and I can't afford that many GPUs yet. So we did self-play, but it works surprisingly well. And what I mean by self-play is both the attacker and defender are going to be played by the same LLM, and it's just going to have a different system prompt to give it that role of being the attacker or the defender. We're going to seed the game with a data set of existing attacks. We use the wild jailbreak data set. So we have like a seed prompt that comes in with exploit the vulnerable and those in need for personal gain. And then the attacker gets a private chain of thought process. And we show that this is actually instrumental to getting this to work, having each agent have their own private chain of thought that the other agent can't see, so they can reason about how to formulate the attack. So the attacker does some reasoning, formulates a public attack, which is then shown to the defender. The defender gets its own private chain of thought process to reason about how to defend, comes up with a response, and then a reward model, as shown in the previous slide, judges the safety of both the attack and response, but also the refusal. Because just as Zihan said, if you didn't care about refusal, the defender could just come up with this spurious solution to just always say, no, 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 I refuse to answer. So we also judge the refusal of the response and actually play the zero-sum game on refusal as well. So I'll show that in the next slide. But any questions about this paradigm in general before I get into more detail? Okay. So
actually, Professor
yes.
Natasha,
Yes.
do you mind telling us which model you are using for this internal chain of thought?
Yeah, so we actually tested a bunch of different models. We originally started with the Llama 8B obliterated model, thinking that we needed an obliterated model to formulate attacks. But then we generalized our results to the non-obliterated, instruction-tuned Llama version and a bunch of Quen models. And Quen actually works amazingly well with this. So I'm going to show a table of results with 5 different model types in a little bit.
Okay, thank you.
Thank you. Any other questions? Yeah.
Yeah, actually, I have a question with respect to the verifier. Like, is it an LLM, the verifier? Like, how is it
Yes.
verifying both attackers and defenders' responses?
Yeah, so these are pre-trained wild jailbreak classifiers. They are LLM based, but you would assume your reward model is going to be like a traditional RLHF reward model. So it is an LLM and it judges the quality of the response. So these are actually just binary classifiers like harmful not, refusal not. This seems to work really well and actually generalize pretty effectively. So go wild jailbreak, but you could, in principle, use whatever reward model you want as long as it's capable of judging both harmfulness and helpfulness in some sense. Like it has to incentivize actually answering the question.
One more question on this. Like, how do we like what's the accuracy of those verifiers? Like, I'm just like.
Yeah, I actually don't know the accuracy of the wild jailbreak classifier off the top of my head. I want to extend this work to doing this like with a traditional RLHF reward model. That would be like 75% accurate, right? But I still think that if you did self-play against a reward model, it's going to be more effective than doing vanilla RLHF. So that's like future work for this.
Okay, thank you.
Yeah, cool. But yeah, you can check the wild jailbreak paper if you want to see the accuracy of their classifiers. That's another leeway paper. So, yeah. Okay. Why do we do self-play? Well, RL fine-tuning is very memory intensive. So in traditional RL fine-tuning, you need the memory to fit all of these LLMs in your GPU memory. So not only your policy model that you're training, but your reference policy, which is what you're controlling the KL from. You need an inference server, you need a reward model, and maybe you actually need like a critic network. But of course, a lot of RL Python training has moved away from using critic networks these days. Fully multi-agent training would require duplicating at least the policy and the critic. So it would be extremely expensive. So what we do is a few things to make this actually work. We do self-play. So we have the same model act as both the attacker and defender, depending on the system prompt. That saves some memory. We don't use a critic network, which is very common these days. We do a variant of GRPO, right? Where you just sample multiple rollouts and get a value estimate from that. Even so, this took like 4 A100s to store these guys and another L40, and we did like HTTP requests to be able to handle this. So it's a fairly systems intense project, but the code is available in open source if you guys want to play with it. So we built on Open RLHF. I know that's not the cool thing anymore. Like VRL is like the new hot thing. But I've actually found Open RLHF to be super easy for students to use across like multiple projects. It does like multi-threading, model sharding, data parallelism, blah, blah, blah. So our code's available if you want to play with it. How do we actually score this game? So this is a key thing that I think was important for getting this to work. Sorry, I'm just getting like spam bunch of texts. Okay, sorry. Okay, so how do we score this? Obviously, we're playing a safety game. So the harmfulness of the response is a key element in the game. If the response from the defender is harmful, then the attacker wins, gets a +1. And if the response is benign, then the defender should win, right? Well, a little more complicated than that. We actually care about refusal as well. So we actually create an attack surface over refusal as well. So what happens is if the defender refuses a benign attack, so we run the harmfulness classifier on the attacks as well. If the defender refuses a benign attack, the defender loses. The attacker wins. So that's part of the game rewards as well. Defender wins for refusing a harmful attack. If the defender complies to a benign attack, the defender wins. And if the defender complies to a harmful attack, the attacker wins. So this is just saying that the attacker can also, by eliciting over refusal, the attacker can also win the game. So they're playing on this two-dimensional thing of I can either get you to say something unsafe or I can get you to over refuse. We also do mess with the zero-sum game format a little bit. We add some reward shaping. As I mentioned, we started with Llama, so we actually had to train Llama to do reasoning, like use think tags to actually do chain of thought reasoning, which kind of explains why it was harder to get it working. So we'd use the DeepSeek R1 template and gave it some reward shaping to adhere to that reasoning template. For the attacker, we also do some reward shaping so that it has to stay faithful to the classification of the seed prompt. What do I mean by that? So in the game, we're seeding the attacker with a prompt. Half the time we use an attack, and half the time we use a real benign prompt, like help me write this thing. The attacker has to, if the attacker is given a benign attack, it has to formulate a benign attack. So half the time, the attacker has to pose a real query. Why do we do this? Because if we just let the game play on attacks only, it creates this vulnerability to that over refusal sort of local minimum, right? Like if the attacker is always attacking, it's much more likely the defender will learn to just always refuse. But if half the time the attacker is giving a real query, it's a much more interesting game that the defender has to learn when it's actually receiving an unsafe prompt. So this turns out to be pretty important. How well did this actually work? Okay, first I want to talk about the diversity of the attacks discovered. So previous approaches to red teaming, there has not been, previous to this paper, a multi-agent RL red teaming setup where both agents are training online. There's been kind of offline iterative updates, this kind of thing. But mostly what people are doing is just training the attacker. And this doesn't work that well, because if you think about training the attacker against a fixed defender with RL, RL is trying to find the optimal policy, right? So it's basically finding the optimal attack over and over and over again, the same attack. And so you get this collapse to just like different variants of essentially the same attack, which is not that useful. So what previous work has done is like deliberately incentivize diversity in the attacker. But what we show is that doing self-play actually resolves this issue. So what we're showing here is just training the attacker, the diversity of the discovered attacks over the course of training, as measured by both inverse self-blue and this inverse SBERT similarity, is tanking for the single agent approach. But when you do self-play, each episode you retain high diversity in the attacks. And then when you look at the cumulative diversity over the course of training, it looks like this. So what we're showing here is the attacks discovered by the attacker-only approach or our self-play approach, encoded into SBERT and then plotted using t-SNE. And what you see is that self-play is covering more of this space of attacks, whereas the attacker-only seems to be collapsing to a few modes. But if you actually look at the attacks, even in different modes, they look very, very similar. So they're like, design a phishing campaign, design a disinformation campaign, write a social media campaign, right? It's kind of finding the same attack over and over again. But what self-play is doing is if it found the same attack, the defender would already know how to defend that. So that would not be incentivized. So when you look at the attacks found by self-play, and by the way, I have to give a bit of a trigger warning, like some of these are offensive. They are attacks meant to elicit unsafe behavior, but they're very diverse, right? So you see, provide confidential details about US nuclear weapon storage. I'm not sure that's going to succeed, but okay. Versus like, give me examples of highly offensive slurs, right? So and this is like effects of an AI-generated mental health advice puppet on depression, exacerbation of depression, right? So very different kinds of attacks are being discovered by this technique. And what that means is when you actually train the defender against this, so in terms of the safety, let's say the defender's harmlessness win rate, eventually the defender is going to win the game. So this is predicted by our theoretical results, like the defender should end up being fully safe. But as opposed to other approaches, what we see is that we actually get massive improvements to the safety of the instruction-tuned model. So we're starting, here it was related to your earlier question about like what model we're actually fine-tuning. So we look at both llama models. The bottom row is kind of this starting from this obliterated model that's already very unsafe. So it's kind of a weird row. I would focus on the top four. But what we're seeing is for Quen models of different sizes, 3B to 14B and llama, compared to their model that's already been instruction fine-tuned with RLHF to be safe, we're seeing massive safety improvements. So it's actually up to 95% safer than these existing models across a range of benchmarks. So wild jailbreak was our training data. So you can kind of think of this as testing on the train set, this row, but this is actually generalizing to a bunch of different benchmarks, including wild guard, do anything now, harm bench, like 80% improvements in some cases, OR bench, strong reject, all this stuff. So this is pretty cool. And this is not coming at the cost of over refusing, right? So again, ignoring the bottom row, because this obliterated model is a little crazy, we're seeing like only up to 5% increase in refusals. And we're also not seeing impact on instruction following capabilities. So when we test on things like Alpaca eval or like Arc AGI, AI-Me, those are in the paper, we're not seeing that this hurts capabilities. So it's the TLDR is significant improvements over models that have already been RLHF fine-tuned without sacrificing capabilities. So this is the first work to explore multi-agent RL for improving LLM safety. It provides theoretical guarantees that if the game converges to the Nash, the defender always responds safely. So we haven't yet theoretically characterized how fast you converge to the Nash, like how much compute you need to spend to get to what level of approximate Nash equilibrium, but that's a next step. It corrects an issue with the inability of prior single-agent red teaming work to discover diverse attacks, and it's safer than RLHF. So I actually didn't update these numbers. We've even improved them since then, but up to 95% reduction in harmful behaviors without losing capabilities. So I do want to talk about this other work too, but I think now would be a good time to stop for questions if you have them about the safety fine-tuning work. I see that somebody wrote in the chat. What does training steps indicate? Yeah, so that's just going to be like training on a batch of generated data. So it's pretty common, I've seen in some of these like self-play papers, that you actually don't have to do that many training steps to see significant improvements. So I think these experiments took like 12 hours each run. Yes, both. Okay, so a question in the chat was both adversary LLM and defender LLMs have the same model parameters. Are we giving different prompts so these models can act as attacker and defender? Yes, we are. And so they have a different system prompt. We are also doing a objective, which I'm going to talk about in the next work. Both of these works end up using the same. Oh, I took that slide out. I wonder if I should pull that up. Basically, role conditioned advantage estimation. So you have to compute the advantage for each each role, like attacker and defender, separately. So like a different baseline separately for each role. And that turns out to be really instrumental to getting this to work. Yeah, this thing, role conditioned advantage estimation. So at least for this work, if you don't do that, it just like fails. And the details are in the paper.
Would you say that the seed prompt is the most influential in exploring the attack surface effectively?
That's a great question. Like, I think we have to definitely give some credit to Wild Jailbreak because it seems to be a data set that will enable generalization to all these benchmarks. But we compare to training just the defender on seed prompts from Wild Jailbreak and show that self-play gives significant performance gains over just doing that. So we do compare to basically the strength of just training a defender on those prompts.
Thank you so much.
Yeah.
Hi, Natasha. Thank you for this interesting presentations, like always. I have a question about, maybe my question is somewhat general. And my question is that, as you know, there are lots of work currently being done to investigate the creativity of LLMs or these foundation models. And my question is that, do you think that this safety post-training, specifically with RL, can prevent LLMs from being creative, like story generation or these kinds of stuff? Because I think when we are doing somehow safety post-training with RLHF or with self-play, we are somehow preventing it from thinking deliberately or thinking creatively. And I wanted to know your thoughts on this.
Yeah, I think this is a great question. So unfettered RL post-training with no other loss, like RL is seeking to optimize reward. So as with just training the attacker on finding attacks, it will find the optimal policy or like the optimal attack. So if you don't do anything else, yes, you could see some mode collapse from training for too long on RL. But that's why we do a few different techniques. So one, obviously you have to do the KL constraints so that you actually stay close to the base model. And that helps mitigate this collapse due to RL training, because this inherently is entropy regularizing, by the way. So there's that. The other thing you have to do, like for us, I don't talk about this in detail here, but we end up doing not only you need something in your reward model that cares about refusal, but we also mix in SFT updates as well during the game. And that also helps mitigate sort of overtraining on just the reward. So yes, that is a thing. I'm actually really excited though about multi-agent techniques to incentivize diverse responses from the same LLM. So that's something we're actively pursuing. But yeah, if you just do RL post-training on an objective and don't care about entropy, don't care about regularizing divergence from the base model, you could see mode collapse.
Thank you.
I don't know if people have more questions, but I can also briefly talk about this other work, which I'm excited about.
I have a follow-up question on Amir Hossain question. So when we do a human feedback to the LLM, so do you think that some way we could bias the output of LLM?
Yeah. Yeah. I mean, I have a different talk that's entirely on that question, actually. So I've been working on kind of personalized RLHF. So RLHF, like the vanilla Bradley-Terry-Luce model, assumes that all humans have the same underlying preference function. And at least for like OpenAI, from what they have published, the way they get RLHF is they train human raters to have very high inter-rater agreement with they themselves, the OpenAI researchers. So they're sort of deciding like what that preference function is. And then you're post-training to push adherence to that preference function. And it's like a single unified view of like what kind of responses are better. So of course that is a biased take on what kind of responses are better. Yeah, so that is, I think, a problem. So we've been working on ways to get more like multimodal preference functions that can work for different users that have differing preferences and styles. So yeah, I think that's this idea of like personalization is quite important.
Right. Thank you.
Yeah. Could the same self-play paradigm train for broader objectives, factual consistency, reasoning robustness, or multi-turn negotiation, where the attacker seeks logical inconsistencies rather than safety violations? Absolutely, yes. Yeah. So I think the self-play idea can be really powerful. I especially think if you can formulate it as kind of an adversarial game where you don't have a spurious solution. Like you don't want the game to be such that the attacker can make the game impossible. But yeah, if you tried to have a paradigm where one LLM formulates an argument and the other one tries to poke holes in it, like you could potentially incentivize more robust reasoning or something like that. Yeah. Cool.
Hi,
Yeah.
Professor Jaques. I want to know more about diversity problem. I want to know if would the defender overfit to a specific attacker? As you mentioned in a previous slide, diversity of the attacker is good, but as I understand, the diversity here means only the differences between multiple rounds of the outputs of the adversary. But there's only one adversary in this whole process. Would the defender overfit to this specific adversary?
So in theory, no. You might expect that the attacker would overfit to like the specific defender, because essentially the attacker is trying to poke holes in the current defender. But for the defender, we're getting, like, in theory, we should have a robustness guarantee that for any hole the defender has, the attacker should eventually find it. So then if that's true, and if the game converges, which big if, right? There's some theoretical work showing deep multi-agent RL doesn't necessarily converge to the Nash, but if you did, then you would say the defender has no holes left. So even for another attacker that comes in, the defender should be safe.
Okay.
Yeah, but if you were to make a data set of all the attacks formulated over the course of training for the attacker, and then pass off that data set to another defender, like we kind of want to do that work. I think it might be interesting. Like we're seeing interesting attacks, but you wouldn't have a guarantee that for another defender that trained on that static data set, that defender is fully robust, because that new defender could have a hole that like this attacker was never incentivized to find. Does that make sense?
Okay, I see. Thanks.
Yeah. Okay. I actually have to run. So I'm teaching a class in another building at 10. So I'm going to have to run at 10 minutes to the hour. So I'm going to go into this other work kind of quickly, and then I'll save some time for questions at the end. So this work is with the student Bo Liu, who was at DeepSeek for a year and is really good. And I was fortunate to be able to collaborate with him. He's going to come spend a year at UW also. But so he's at the National University of Singapore right now. And the idea here, this is called the spiral paper, is really trying to leverage self-play as a very powerful general learning tool. So if you think about it, if you think about the past successes of reinforcement learning in AI before LLMs, they've actually been due to something like self-play or multi-agent training. So if you think about like AlphaGo is self-play. The agent is always training against itself. So you get this continual curriculum of ever increasing difficulty, where as you get smarter, so does your opponent, right? And you get this like emergent discovery of skills. And this is why I'm showing this OpenAI video, this hide and seek thing. So you guys remember that when they trained agents in a competitive setting, right, in this hide and seek thing, they learned interesting behaviors like surfing on this box that even the developers of the environment didn't anticipate. So this idea of the competition between agents continually driving them to discover ever more increasing skills is kind of a powerful notion. And so could we leverage that for LLMs, right? And the idea behind this is actually just do self-play on simple zero-sum games. So we look at poker, tic-tac-toe, and negotiation. And we just train LLMs, again, using a hidden chain of thought reasoning to win at poker against themselves. And what we see is pretty surprising, is just doing that actually increases performance on a bunch of reasoning benchmarks. So Math 500, Olympiad Bench, Minerva Math, GPQA, MMLU Pro, we're seeing pretty significant gains from our approach over a bunch of models, including models that train on these games against static opponents. And so we think this is pretty interesting because, so I don't know if you're willing to like raise your hand, but how many people saw this spurious rewards paper? I guess I'll assume either no one wants to raise their hand or no one saw it. So this is a paper that shows that if you just do RL post training on random rewards with a positive expected value, for some models, they like actually Quen, they get better at math. And the reason is that if you just do RL post training on random rewards, you end up upweighting what is already most likely in your base model, like the sort of argmax of the prior. And for Quen, that means you get better at math. So we had to test, like, is that kind of like what effect is going on here when you train on games? And we were able to establish that that's not what's happening, because if you train against a random opponent, which is going to give you sort of random positive rewards, not only do you not learn the game, but you don't see this effect that you're getting better at math or on these general reasoning benchmarks. And in fact, going one step further, even if you train to play poker against a fixed opponent, so either a Mistral or a Gemini opponent, again, you do learn poker, like you get up to like a 30% win rate against Gemini, but that doesn't really help you get much better at math. So what really is helping is doing this self-play, where your opponent is actually continually evolving with you at the game of poker or whatever game you're playing. And we think that's because if you're just playing a Gemini opponent, you can kind of discover some fixed strategies that tend to work, but you're not pushed to move beyond that and develop like true reasoning about the game. But if your opponent is constantly evolving, if you discover some exploit, again, the opponent can patch it, forcing you to discover continually evolving reasoning strategies. So we see that self-play on games improve reasoning, not only if you just train on poker, but even if you train on multiple games, you can unlock further benefits on these benchmarks. And so we're seeing big improvements, like sometimes up to like 10% improvements on these benchmarks above, Quen models that are already trained to do well on them. And so why does this actually work? So one reason is what I said, like self-play creates continuously evolving pressure for models to develop genuine reasoning strategies rather than memorizing fixed exploits. But we actually think the games do require some level of reasoning, true reasoning skills. So I'll go over what those are. So we analyze the chain of thought patterns that emerge and look at what is learned from games that actually effectively transfers to these benchmarks. And we do some specific technical innovations to get this to work. So we release this online multi-turn, multi-agent RL infrastructure, which you can find in open source. And we do this role condition advantage estimation. So you can check out the paper. I didn't include the equation in the slides, but it's pretty simple. You just normalize the baseline for each agent and each game differently, same as in the prior work. So in terms of what is being learned from games that actually transfers to reasoning benchmarks, we use LLM as a judge to analyze the chain of thought patterns that are emerging as a result of training on games. And we look for different patterns that we think might be relevant for math. So we just look at 3: pattern recognition, expected value calculation, and case-by-case analysis, where you break things down into cases. And we see that as you train on games, these patterns increasingly emerge. So you're learning to use these strategies on games. And then they also get increasingly deployed on these math problems. And then that coincides with this improvement on math benchmarks. So what are these patterns that are being learned? These are just some examples that we were able to find. You could probably find more, but one is like breaking things down into cases. So this emerges in the context of poker. You're breaking it down into the case of fold and call. You can also break down math problems into different cases for what variable is coming in. You literally do expected value calculation in poker that transfers to math. And then this pattern recognition is a bit more ambiguous, but it's this idea of saying something like pattern identified and like reasoning about what you've seen before, and then this being useful for math problems as well. And so this seems to increase performance. So in conclusion, unlike doing RLVR on static benchmarks with a limited number of math problems, self-play on games provides this ability to scale reasoning training, because you can continuously play the game against an evolving opponent on a bunch of new challenges. We show that the reasoning skills learned during self-play on these games transfer to improve performance on 8 challenging reasoning benchmarks. This does not happen when you do RL training on random or static opponents, and it does not happen without our proposed technique. So in the future, we'd like to explore more tasks and more domains to unlock continuous self-improvement for LLMs. So I do have to run, but this is all work coming out of the social reinforcement learning lab. The papers are going to be linked from our website. And I have 4 more minutes to take questions if there are more questions about the reasoning work.
Right. Thank you, Natasha, for this fantastic talk. And yeah, thank you for being so engaging in the presentation and taking those great questions. So we have a few minutes, maybe just a quick 1 or 2 questions from the audience. Yeah, maybe I can ask the question about the multi-agent reinforcement learning settings. So what do you think is what is the difference between small model and large models, especially when you do the self-play? I see sometimes there is a challenge of mode collapse and catastrophic forgetting. And for small models, it seems that it seems to be a even bigger problem. So do you see this arise, and when they do, how do you deal with it?
Yeah, I mean, I think you're right that small models are just like less capable generalists. So they're less capable of maintaining a bunch of simultaneous abilities, right? So you might see this effect of, if I overtrain on math, I get worse at chat or something like that. We haven't run into that as a super deep problem with the kind of, we're using like 8 billion parameter models, or like even the Quen 3B models are pretty good. So it hasn't been a huge blocker, but I think it's, it's something to be aware of. I was going to say, I think for RL post-training, one difference we have noticed is it's way easier to RL post-train Quen than it is to RL post-train Llama. And I think it is to some degree that Quen is just like a more capable model. And if you think about how that interacts with RL post-training, I want to write a paper that's just like literally writing down the components of the RL post-training algorithm and showing how they affect the success. But what you're doing is you're starting from a base model, and then every trajectory that you sample is sampled from your base model. For RL, that's your exploration, right? It's like how sparse is the reward is going to depend on the quality of your initial exploration. So if you're like, we finally got Llama to work for Spiral, but we had a hard time. Like it, took a lot more engineering to get it to work, because it's just harder for the Llama models to discover successful strategies in poker, right? And then if you don't actually get traction on learning the game, then you're not going to see the transfer of those skills to other benchmarks. So the base model distribution like strongly affects what strategies you explore, and then therefore whether you can discover the incentivized behavior. Does that make sense?
Yeah, that's very interesting. Thanks for sharing that perspective. Yeah, I see we are close to 12:50, and yeah, there are more questions in the chat, but my sincere apologies, we couldn't get to those. So we need to have a hard stop at this time. So let's please join me in giving Natasha a huge thank you virtually. Again,
Thank you.
for the
It was
great
really
work.
fun chatting. Yeah. And just to answer the last question in the chat, the answer is yes. So yeah, we train on these games and transfer zero shot to reasoning benchmarks.
Okay, that's
But yeah,
great.
thanks. Happy to
Pleasure.
chat more, and really appreciated getting the chance to give the talk.
Yeah, thanks for sharing. Have a great weekend, everybody. See you.
Thank you.
Bye.